Here we go, a little bit more on infinity. So we have a new object that we're going to call improper integrals. And we're looking at a particular type of improper integral in which the integrand, and if you recall, the integrand is the function that you're integrating over, is infinite. Well, that's going to happen when you have a vertical asymptote. So that's why they're called improper, is because we have kind of different issues going on. If we look at this integral, we've got a problem here. If we look at this integral, let's see, our problem's down here. And if we look at this last integral, our problem is sandwiched in between the two endpoints. So first we'll just quickly run through and talk about how they're officially to be written. So these are improper integrals, so to write them appropriately with a limit, we would actually, because this is our problem child, we would really say, and I always like to use A and B because that's the traditional ones, we instead would really say this is the limit as B goes to 2. But when we look at this interval between 0 and 2, we know we have to come at this interval from the left side of 0, to B of f of x dx. So on the next one, our problem child is down here, and now we're looking at this interval. And so now when we look at our problematic piece, it's on the right side. It's on the left side, and we have to come at it from the right side in order to, go over a continuous interval. So this really, we can write it as a limit. So A is going to go to 2 from the right side, because that will keep us within a continuous interval. So we're going to go from A to 5. Because this one has the problem child smashed right in between it, first we're going to break it up, because you can't go over a discontinuous function. So we'll break it up to 0 to 2 plus 2 to 5. And then we really need to write these as limits. So the problem child on this one is here, and here it's over there. I'm down there. Sorry, it's late, I'm tired. So here we're going to write this as the limit as B. I'm going to choose B because it's the upper limit of integration. Goes to 2, and if we're looking at 0 to 2, we're coming at that 2 from the left side of 0 to B, plus, now there's our problem, so the limit as A goes to 2, and now we're coming at it from the right side of A to 5 f of x dx. This is very formal language. When you're actually doing these problems, you rarely take the time to write out all these limits, but you certainly should recognize it, and you should be able to do it if necessary. I like to use A and B always as my lower limit of integration and my upper limit of integration. So that way I just need to know which one I need to replace. So you look for your problem child, figure out where it is you need to replace, and you know that you're always going to be approaching A from the right side, and you're going to be approaching B from the left side, because that was what would give you that continuous interval. So let's do a problem. So we look at this, and we'll go ahead and write it with the formal way one more time. And so we look at this and we go, let's see, our problem child is down here, so I'm going to call that my A. So I'm going to rewrite this, as a limit as a goes to 0 from the right side, the a is always from the right side, of a to 1 over x dx. Well, when we do this, I'm going to suggest right now a shorthand already. So this is our issue. And so I'm going to do this. We know our antiderivative is ln of x. And I'm going to say, so my lower limit of integration is 0 from the positive side. That will remind me that this thing is technically a limit, because I only have to worry about that limit being troublesome if it's indeterminate. Because for most limits, we can just plug it in and it can be a perfectly valid answer. So our first line of defense is just to plug in that 0. It's only if we get an indeterminate form that we're going to have to break that out and look at it as a limit. So from 0 from the positive side to 1, so that's going to be ln of 1 minus ln of 0. Oh, that's a problem. So we've got 0 minus negative infinity. But it's not indeterminate. It just does not exist. So that thing as a limit does not exist. And what we say when that limit does not exist, when we complete this algebra, is we say the integral diverges. Geometrically, that means the area under this curve, underneath 1 over x from 0 to 1, is infinity. Well, maybe this is a useless lesson. I mean, wouldn't you think that the area under any infinite place where this goes shooting up to infinity would be infinity? Let's try another one. So how about this one? So now we're going from 0 to 4 of square root of 1 over 4 minus x. Curve looks like this. I thought I'd save a little bit of time. These videos are long and boring as they are. And so I'm going to jump right to the shorthand. Let's see, I'll have a chain rule of negative, add a power to the 1/2, divided by 1/2, so it's going to be negative 2 root 4 minus x, and I'm going to use my shorthand. I know that this is my problem child, so that's the one that I'm going to give the little right or left hand limit to. 0 is perfectly good, but I'm going to be going to 4 from the left side. So the upper bound is always from the left. So when we plug that in, first thing, we'll just plug it in and see if we have a problem. Negative 2, we plug in 4. We don't have a problem because the square root of 0 is a perfectly valid number. It's 0 minus negative 2, square root 4 minus 0. And square root 4 is 2, 2. Oh, it's 2. Oh my goodness. That looks like an infinite area, but the area under that curve, that yellow area, is actually 2. And we say the integral converges to 2. So converge and diverge are 2 new vocab words for us, but we'll be using them a lot, so you'll get very used to them. Let's try another one. How about this? Oh, ln x has an asymptote, so we can look at that. And if we're going from 0 to 1, let's see, our problem child is right down here. And so I'm just going to kind of like use my shorthand to write it out so that I'm not spending so much time doing boring writing when we could be thinking about mathematics. So, we're going to need a voodoo. So u equals ln x du 1 over x dx dv dx v x uv. So x ln x minus x times 1 over x is just 1, so dx. So it's x ln x minus x There's my problem child, 0 from the right side to 1. Let's take a look at what happens. So I'm at 1 times ln of 1. Oh, that's 0. I'm just going to jot that down. Minus 1. And now minus, when I plug in 0, 0 times, oh, ln of 0 from the right. Oh, that's negative infinity. Minus 0. But here we go. That's an indeterminate form. So that indeterminate form needs to be figured out as a limit. So hopefully we're getting used to this, and we kind of like the 0 times infinities because all we have to do is rearrange them. So we know we've got x, ln x, and we need to rearrange it into a fraction. So I'm going to put the ln of x on top. That makes my chain rule so much nicer. Basically don't have a chain rule. So I'm looking at the limit of ln x over 1 over x as x goes to 0 from the positive side. And so now I've got infinity over infinity. I'm ready to L-hop. Limit as x goes to 0 from the positive side of 1 over x over negative 1 over x squared. Oh, that's cool. Limit as x goes to 0 from the positive side of negative x. Oh, that thing just equals 0. So what we have here is we've got negative 1, negative 1. So that integral converges to negative 1. That means this region is like negative 1. I don't know. I think it's kind of cool. Let's try another one. Let's look at this. So, wow, we're over at 12 minutes already. So let's take a quick look. And so here's our picture. And let's jump right to the antiderivative. And so the antiderivative, add a power, divide by the new power, but plus there's a negative for the chain rule. So it would be negative, but then we've got another negative from the chain rule, 3 minus x. And our problem child is right in between. Oh, so really I need to break this thing up. So I'm going to change it into 1. I'm going to change it into 1 over 3 minus x. And I need to go from 1 to 3 on the left side plus 1 over 3 minus x from 3 on the right side to 4. So when we plug in 3, yeah, we've got a problem. And let's think about this. 1 over 3 minus x. Let's see, and the x is negative, so it's going to be this. So as I go, the limit of this, as I go to 3 from the left side, that's going to be infinity minus, now I just plug in 1, minus 1/2, plus, now I'm going to 3 from the right side, so now I'm on this branch of the hyperbola. So that one is going to be, oh, I jumped the gun, sorry. When I plug in 4, I'm at negative 1, and then here's my FTC, minus, when I plug in that 3, I'm at negative infinity. Oh, look, I don't actually have an indeterminate form. I have basically infinity minus 3/2. That's actually not indeterminate at all. That just means the integral diverges. And we are already at almost 15 minutes, so I'm going to have to figure out Loom. I've been avoiding it. And so I am going to leave this for you to do. You'll notice that I did this video kind of late in the evening, and so I printed up the notes for you all.